Good afternoon. Today we will continue with the second unit topic, which is mathematical induction. This topic is something which you have already studied in the earlier classes in a great detail and also have given proofs for the mathematical induction problems. Now today we will see the same proofs that you have already studied earlier, but also why is it useful in discrete mathematics. So mathematical induction is basically whenever a property states that your formula is true for all positive integers, and that kind of property is proved if the proof is given by showing that the statements hold for some positive integer, and also it should be true for the next larger integer. So mathematical induction is based on the rule of inference. So it is based on the rule of inference, and it basically means that if P of 1 is true and for every k, P of k is true implies P of k plus 1 should also be true. Okay, so if the domain is the set of all positive integers. So mathematical induction can be used to prove a tremendous variety of results, and it also explains us how to read and construct the mathematical induction goals in discrete mathematics. So let's start with our chapter. Let's start with our topic mathematical induction. So as an example, suppose if we have an infinite ladder as shown in the picture here, then we can reach the first rung of the ladder, or we can reach the first step of the ladder. Then if we reach the first step, then we can reach a particular step also, and then we can reach the next step after that particular step. So basically if we reach the first rung or the first step, then we can reach the second step, and we can keep on doing this until we reach some step which is k. Okay, and once we reach this step k, we can also reach k plus 1. So first and foremost we have to reach the step 1, then we have to reach step k, and then if we reach step k, we can also reach step k plus 1. This example basically is the mathematical induction. So this example is the best way to represent mathematical induction. Now let's see the principle of mathematical induction. So principle of mathematical induction: to prove that P of n is true for all positive integers n, we complete these steps. So if P of n is your statement, then to prove it is true, we show first P of 1 is true, and then we show P of k implies P of k plus 1 is also true for all positive integers k. So P of 1 being true, that is known as a basis step, and inductive step is if we show P of k as true and then we show P of k plus 1 to be true also. To complete the inductive step, assuming the inductive hypothesis that P of k holds for an arbitrary integer k, then we must show that P of k plus 1 is also true. So climbing an infinite ladder is one example. We can reach the first step, then we can reach k step and also k plus 1 step. Okay. Similarly, to remember how this works, consider an infinite sequence of dominoes. What were dominoes? Dominoes were basically the a rectangle which can be placed on two tiles in a checkerboard. Okay, so if you're talking about dominoes and each of them is standing in this way with numbering written on each of them, 1 2 3 and so on. So if P of n be the proposition that the nth domino is knocked over, so if we knock P of 1, then it will knock P of 2, and we have some domino k over here which has fallen down. So if k has fallen down, then it means the next integer after k has also fallen down. So this is how your mathematical induction works. So we have to prove for P of 1, then we have to assume that P of k is true, and then prove for P of k plus 1 to be true. Okay, so this is your mathematical induction working. Now let's see an example with the same. So we have to show that n is equal to I is equal to 1 to n is equal to n plus 1 by 2. So for this, let's prove this by using the mathematical induction. So if the given formula for the given example is given as, we have I is equal to 1 to n into n plus 1 by 2, or it can also be written as 1 plus 2 plus and so on up to n numbers gives us the result n into n plus 1 by 2. So if P of n is the proposition that sum of first n positive integers is n into n plus 1 by 2, then we must do two things. Okay, so to prove that P of n is true, we have to first check for P of 1. What will be P of 1? P of 1 is 1 into 1 plus 1 by 2. Okay, so this gets cancelled. P of 1 is 1. And what is the first term? It is simply 1. So P of 1 is, this P of 1 is taken as is true. Now we have to prove for P of k. So P of k, we assume it is k into k plus 1 by 2, while here summation is 1 plus 2 plus and so on up to k. Now under this assumption, we have to take P of k plus 1. So P of k plus 1 is taken as, here P of k plus 1 is equal to, or it can be written as 1 plus 2 plus and so on up to k plus 1, which will be equal to, instead of our formula of n into n plus 1 by 2, instead of n we were substituting k plus 1. So let's write it, k plus 1 into k plus 1 plus 1 by 2. Now this is written as k plus 1 into k plus 2 by 2. Okay, this is also considered true. Now how should we take it? So when we add, if we have our P of k will be 1 plus 2 plus and so on up to k is equal to k into k plus 1 by 2. Okay, this is our P of k, which was assumed as true. Now to this equation, add k plus 1 on both sides. So once we add k plus 1, this can be written as 1 plus 2 plus and so on up to k plus 1 is equal to k into k plus 1 by 2 plus k plus 1. Okay, so now this we will continue it over here. So if you notice, we have the equation that I have just written is the same over here, 1 plus 2 plus and so on up to k plus 1, and then we are adding k plus 1 here on both the sides. So this has been added. Now for this, we have to take this side and take the complete LCM, k into k plus 1 plus 2 into k plus 1 by 2. Now we get k plus 1 into k plus 2 by 2. Now this was similar to what our P of k plus 1 is. P of k plus 1, if we substitute in place of n, we will get k plus 1 into k plus 2 by 2. So if both of them are equal, then P of k plus 1 must be true. So the induction that P of k is true is true. So our basis step, P of 1 is true, and our inductive hypothesis P of k, if P of k is true, then P of k plus 1 is true is also correct. So this proves our mathematical induction for I is equal to 1 to n, I is equivalent to n into n plus 1 by 2. Similarly, you can solve any kind of formula with this. So over here, I will show you another example, which is for the series. Show that we are supposed to prove 1 plus 2 plus 2 square plus and so on up to 2 power n is equivalent to 2 power n plus 1 minus 1 for all positive integers. Okay, so for all z plus values. So our basis step will be, since we have here 2 power 1 and 2 power 0 also, so we have to show for p of 0 is true. Why? Because 2 power 0 is here, 2 power 0 is 1, and also this side if we take over here, then this can be written as 2 power n value is 0, 0 plus 1 minus 1, which is equivalent to 1 again. So this completes the basis step. 2 power 0 is 1 and this is also 1. Now we have to take our inductive step. For inductive step, first we have to take P, assume that P of k is true. So this is our hypothesis. Hypothesis is assumption or premises, and this assumes that P of k is true. So if we assume P of k is true, then we are supposed to assume that P of k plus 1 is also true and prove it. So for P of k plus 1, we will write it as 1 plus 2 plus 2 square plus and so on up to 2 power k, and then we have to add 2 power k plus 1, and instead of n we are supposed to substitute 2 power k plus 1. So k plus 1 plus 1 minus 1. So this will be equivalent to 2 power k plus 2 minus 1. So here if we assume the inductive hypothesis P of k is true, so we are adding 2 power k plus 1 on both the sides. Or else we can do it this way, 1 plus 2 plus 2 square plus 2 cube and so on up to 2 power k plus 2 power k plus 1 is equivalent to 1 plus 2 plus 2 square plus and so on up to 2 power k plus 2 power k plus 1. Now over here, this entire thing is your P of k. So P of k can be replaced by this statement. P of k is 2 power k plus 1 minus 1. So we can replace it by 2 power k plus 1 minus 1 plus this 2 power k plus 1. Now after that, we are taking this 2 and we are writing it as 2 power k plus 1 minus 1, because we have 2 power k plus 1s. So it will be 2 into 2 power k plus 1. If we add this 2 power 1 a power m into a power n, it will be written as 2 power k plus 2 minus 1. So if we have 2 power k plus 2 minus 1, this is your k plus 1 plus 1. So this is P of k plus 1. This holds true. So obviously P of k is also true. So we have seen two different kind of mathematical induction problems.